Just a disclaimer to start. Please note I am not a licensed financial advisor or registered investment advisor. Any and all of the information provided or otherwise made available to you is for informational and educational purposes only. None of it is financial or investment advice, and none of it shall be construed to be financial or investment advice. To the extent that I share any viewpoint, it's just my opinion and subject to error, inaccuracy, and inconsistency. I am fallible. I do not guarantee any particular outcome. Please do your own research and decide for yourselves. Thanks. Hi guys, thanks so much for all of your very nice comments on part 2 of this series about Constellation DAG. I had recorded a part 1, but I decided that in order to do justice to Constellation, I would go back and re-record parts of part 1 that I felt were inadequate and didn't properly explain some of the fundamental aspects of the technology. So this part is a re-recording of part 1, and the focus of this video is the technology in Constellation DAG, focusing on the more technical side of DAG and the logic of its design. So thank you very much again, and thanks to all the Constellation team for their really kind shout-outs and retweets, and I hope you enjoyed this video. Hi guys, so this video is about Constellation DAG. It's quite a complex technology, so what I'm going to try to do here is to compress it down and simplify it into a video that's hopefully only a few minutes long. So Constellation DAG is blockchain for big data. DAGs are distributed acyclic graphs. DAG actually stands for directed acyclic graph, not distributed, but in the case of Constellation DAG, the graph is actually distributed out amongst the devices. So just an error there when I call them distributed. DAGs are structures that are used in big data for high volumes of data, and they're used in consumer applications like Twitter. And so what Constellation are doing is leveraging this data structure in a blockchain context. As far as I'm aware, there are no other companies in the blockchain space that are really focused on big data. But that doesn't mean that their technology is exclusively used in the big data context. They can do much more than just what's in a big data vertical. So it's a very interesting technology, and there's lots of things in the white paper which suggested that there was like a level of depth to this that is quite unique. So what was the problem that they're addressing? The problem is the same problem as all blockchains, which is honor amongst thieves. How do you provide a way for anonymous parties to perform transactions without a middleman in a trustless setting? That's the problem space, as it were. This is also characterized as the Byzantine generals problem in computer science. And this is the problem where parties must agree on a single strategy in order to avoid complete failure, but where some of the parties are corrupt and disseminating false information or are otherwise unreliable. The blockchain was a solution to this because it effectively enabled trustworthy communications in a trustless setting. The blockchain works because it is a distributed record of all the transactions that are taking place on the network. Because all of the nodes have the same ledger, that means that inconsistent or duplicative transactions in that ledger are not possible because all of the nodes are checking the ledger constantly for consistency. The nodes in the blockchain network then synchronously update the ledger with new blocks. The fact that it's synchronous means that malicious actors can't exploit the time lag in updating blocks. So the way that a blockchain ensures that the nodes are trustworthy is that it effectively requires them to have skin in the game. There are two different ways traditionally that this is done, proof of work and proof of stake. And the way that the nodes in each case have skin in the game varies a bit. You can have carrots and sticks. So you can have sticks in the form of the computational resources it costs to participate in the network, but also carrots in the form of the rewards that nodes earn from securing the ledger. So for a blockchain, its strengths are also its weaknesses. That is to say, a A blockchain is a highly redundant record of the transactions. This is because each node hosts an entire copy of the ledger, which means that all the nodes can go offline or break, but as long as you have one node remaining, then you still have the whole ledger. So that makes it highly redundant, but this also makes it highly inefficient. Because all the nodes are working at the same block height on the same ledger, you have a high degree of concentration of the computational power. So there's concentration really in three separate respects. First, you have all of the nodes working simultaneously on the same target, the same block height. So all the available computational power is targeted at one space in one temporal window. The throughput limitation is a fundamental non-trivial problem. It arises due to the abstract geometry of a blockchain. A blockchain has two ends, but only one business end, i.e. the current block that nodes are working on. And so that means that all of the computational resources necessarily must be focused on that block. And this is the case regardless of how much computational power you add to a network. You're always going to be faced with this limitation. Likewise, you can delegate the workload off-chain, the computational work off-chain, and perform consensus on smaller amounts of data or more compressed hashes of that data. But you still haven't resolved this fundamental problem. You've just made the blockchain more efficient, but you haven't made it more effective, right? You cannot circumvent this limitation. It is baked into the geometry of blockchains and is going to exist regardless of how much computational power you add to the network. So Constellation is interesting because it inverts these limitations and turns them into strengths. And it addresses this problem at the requisite level, that is, at the geometric level. The core innovation of Constellation is that it conducts asynchronous consensus in a directed acyclic graph. And this wouldn't be possible in a blockchain. And what it means is that you can have spare nodes such that their computational power can be used elsewhere at a given time. You have parallel consensus, which means that you can have separate chains forming at the same time. And this follows from the fact that there are spare nodes that is possible. And thirdly, you can have a division of labor. You can distribute the workload amongst nodes in a more optimal way. So this is the fundamental solution, changing the geometry itself from a linear blockchain to a directed acyclic graph. So in the technical white paper, they say asynchronous or concurrent processes are the backbone of scalable programming because it allows all of the resources of a computer to be used, speeding up overall computation. So you can see they have a visual representation of how this creates greater throughput through adopting a DAG instead of a blockchain. In a blockchain, you've got a fixed throughput represented by the area of the pipe, and then you've got a directed acyclic graph where you've got many pipes representing many blockchains at the same time, essentially. So that's sort of like the core linchpin factor here. By building data structures around this capacity for asynchronous consensus, you have much more efficient throughput. How do they achieve this asynchronous consensus? What they do is they devise a schema for specialization of function amongst nodes. So you can read more about this in the technical white paper, but basically they have stars, which are like the basic nodes, then clusters, galaxies, and black holes. The nodes can be more lightweight. You can have stars that are mobile devices like your iPhone or something like that. And what happens is that the DAG actually uses a machine learning algorithm to engage in automated federation. So here's a passage that explains this a bit. They note that generally the optimal arrangement in network theory is known as scale-free, which is a hierarchical arrangement with large central nodes orchestrating many smaller peripheral nodes. This arrangement is seen in nature and most notably the internet. So here you can see what they mean. In a traditional blockchain, you can see the nodes are performing consensus on this linear chain of blocks, and all the nodes sort of have the same function. Whereas here what you have is light nodes on the exterior which essentially enable greater space and therefore greater throughput. So let's talk a bit about data. Data is the fundamental unit in the DAG. The original Bitcoin blockchain, what you have is accounts and balances of Bitcoin. Bitcoins are just quantitative units, monetary units. Then you had Ethereum, which was about smart contracts, which are code in the Ethereum virtual machine. And then you got ERC20 tokens and other tokens like NFTs. And that was the ontology, that was the basic units and operations in Ethereum. But what you have with DAG is essentially a very clever recognition that really it's all data under the hood. Like when we're talking about Bitcoins and we're talking about Ethereum smart contracts and ERC20 tokens, we're always talking about data. Like in the virtual world, it's all equivalently data, right? When you check your bank balance online, you're looking at data. Everything can be modeled by data. And I think that's the real magic of Constellation DAG and L0. That's what makes it interoperable, because it essentially can represent everything that is represented on other blockchains and in legacy data systems. It has this pliant nature. Data is quite special in that way. It's a special category because it can be used to represent virtually anything. They draw on something called type theory, and they use bundles of data. I don't want to go too much into that rabbit hole. Basically, what you need to understand is that the hypergraph deals in terms of data, which it bundles together, and those bundles have consensus performed upon them and also point to other bundles, and by virtue of that perform consensus on those other bundles. And it's important to emphasize here that the nodes actually perform consensus on the data itself. The hypergraph tracks data around and performs consensus on it at every interval as it's being transmitted. That's essential for cybersecurity purposes, because you need to protect data at every stage of its path through the hypergraph. Otherwise, you're susceptible to man-in-the-middle attacks and spoofing of data. If it's not protected throughout, then you've got a sort of critical fault, which basically ruins the whole promise of cybersecurity. And because the data also includes metadata about the devices that it passes through and where it came from, it proves the authenticity of the data. And that's related to how they solve the oracleization problem. They show where data comes from. They validate it at origin. And so because it's validated at origin, it's a solution to the oracle problem, which is how do you validate data and get it into a smart contract or onto a blockchain. Now, let's talk a bit about the data structures that fall out of this consensus. I'm just going to read out this passage which explains why they use tetrahedrons, but I basically think this is a stroke of genius. So they say we use 3 nodes in each consensus round because it gives us some interesting mathematical processes for reasoning about state by forming a surface plane across data in the form of tiled triangles. The protocol then uses the triangles to stitch together an optimal surface that is free of redundant or conflicting data and has the minimal triangles possible. It says this shortest path is equivalent to the optimal storage of data within the DAG. If you're trying to understand why triangles, another way I think of it is like when you have 2 devices or users engaging in a transaction, you have then a third to oversee that transaction and what's happened. And that's a sort of heuristic I use to think about why they use triangles. You get tetrahedrons when you triangulate the triangles. You join the sides of each triangle to each other triangle. And that's basically what the hypergraph is composed of. It's composed of tetrahedrons. I wrote a tweet about this a while ago, and it reminded me of Buckminster Fuller, who was an unsung hero in American history. And he also was inspired by nature in creating his inventions, and he invented all sorts of unusual things. He believed that tetrahedrons were the most basic units of space because they are the minimal amount of points you need in order to create a volume, right? You need a minimum of 4 points. So it encloses the least volume in the greatest surface area. And so using tetrahedrons in the hypergraph for me seems theoretically optimal because it has the most surface area and can hold the most data. So here you can see Bucky himself, and behind him is the geodesic dome, which was one of his most famous inventions. And this is composed of triangles that form a sphere, and it has an inherent structural integrity, which Bucky called tensegrity, which was like tension and integrity. A key thing to note here is that a directed graph is a DAG if and only if it can be topologically ordered by arranging the vertices as a linear ordering that is consistent with all edge directions. Topology is the study of surfaces and deformation. You might have heard of the coffee cup donut morphism in topology. Basically, that's important in a blockchain context because transaction ordering is everything. That's key to solving the double spend problem. You need to be sure that you've got the order of the transactions correct. Again, this speaks to how Constellation have addressed the problem at a fundamental geometric level. They've adopted a data structure that preserves the order and relationships of the data and data transmissions within it. So that's how you keep all of the tetrahedrons mutually coherent. But let's now look at how they deal with conflicting data through their consensus mechanism. Constellation uses a needful meritocratic consensus. So what does that mean? Well, first it means that it only performs consensus where there's a conflict in the data. The nodes basically will start engaging in consensus and querying adjacent nodes and cross-checking the information that they have. So it's needful, which is an interesting distinction because most other blockchains don't adopt that approach. They perform consensus presumptively, right? It's the default, whereas here it's not the default. And so also something to note here is that the nodes in the hypergraph can be sleepy, basically that they aren't always performing consensus. They're sort of activated when necessary, and obviously that's optimal. You're not constantly running nodes and eating up energy and computational resources. The other thing to note about their consensus is that they use proof of reputable observation. They also call this proof of mean. And basically what this does is it assigns a reputation to the nodes based upon their performance. Proof of reputable observation, PRO, is a meritocracy, whereas proof of stake is a plutocracy because it's governed by who has the most wealth. There's obvious problems with proof of stake, I think, that you basically have a centralization of resources and power, right? Which means less decentralization and therefore less trust in the blockchain that you're using. So how this consensus is applied to the hypergraph is that where it detects a conflict, it will prune off the triangle that doesn't fit and remove it from the surface of the hypergraph, like shaving it off. And it uses a machine learning algorithm to adaptively score nodes as they perform and they update them. This is the name of the reputation module that they've used. Another thing to note about the consensus is they use a gossip protocol. So nodes gossip around the data to neighboring nodes. And part of their meritocratic consensus in that context is that they use this principle of you're only as good as the company you keep. So this relates to how each node is both performing consensus, but also having consensus performed upon it by its neighbors. After a node has been validated, that node is then trustworthy and can be used to validate the state of other adjacent nodes. This is possible because reputation is transitive. We could say that it is a form of derivative consensus, a cascading consensus among adjacent nodes, or meta-consensus. It leverages the fact that reputation itself is stateful. You can compare this to the traditional proof of work and proof of stake protocols, where the nodes do not remember the prior history of other nodes. They are relying entirely on the present skin in the game that the nodes have. So here you can see something that uncannily looks quite like a black hole, and that's one of the terms that they've used to describe their nodes. You've got information being passed through the hypergraph, trying to make it through this funnel. If it's not getting the right treatment by the nodes, then it gets cut off. And I should say, in that event, it doesn't mean that the data is like just lost. All that happens is that the transaction will have to be resent. So it's not like there's some sort of irreversible consequence to that happening. Now let's talk a bit about state channels. And this is Constellation DAG's answer to smart contracts. You could describe state channels as smart contracts on steroids. And in the light paper, the team say our approach to application support can be thought of a decentralized smart contract platform. Instead of a central network executing all logic and processing, Constellation orchestrates application data with state channels, which can be thought of like a television station. Okay, so you can think of a state channel like beaming the state of a system to another endpoint. And so that is an ongoing state of communication about how a system is at a given moment in time. What you have is a serverless architecture where you are plugging into the hypergraph and the state of your system is being transmitted across the hypergraph in a serverless fashion. It could be an account balance, it could be information from an IoT device. Each state channel can implement its own validation logic. You're not bound into any sort of economic relationship. You can define it yourself. The only thing is that you do, if you want to mint tokens on the hypergraph, that does require DAG. But other than that, you have a lot of freedom in terms of how you define the economies in your application. And this is why they liken DAG to WordPress, because WordPress was a template used that enabled people to define in the format and introduce application logic to their websites. It enabled and empowered people to do that. And DAG is giving people that freedom, but in the context of blockchain. You can compare that, I suppose, to like Ethereum. When you use Ethereum, you have to use the ETH tokens to pay network fees to the extent that you're interacting with the Ethereum virtual machine. That's a hard constraint, but it's not the same with DAG. You have much greater freedom in terms of how your tokens work and how the economies between users in your application work. Here they talk about what makes this a high-low chain. Their approach to application support uses the functional programming model of recursion schemes. It basically enables anyone to put data in there and pluck it back out from the state channels. That's really all you need to know about that. Let's talk a bit about its microservice architecture. It uses the Java virtual machine instead of the Ethereum virtual machine. One of the things they point out is that when you're building on Ethereum, you need to learn a special programming language, and that obviously is a bit of a barrier to entry for new developers. Java is more familiar to developers in general, and so that's an advantage for trying to onboard new developers. All the state channels form composable microservices, and this basically means that they're like Lego blocks. Ethereum often talks about Lego blocks and composability, and the same thing applies here. And what Constellation DAG enables is a sort of serverless architecture that allows for the provisioning of resources for applications. So when you're building an application, you can use some of these microservices by plugging into state channels as necessary. And you can access resources in a way that involves low latency. This is like edge computing. You have databases and content and services located in a server that's near the user, which enables them to load up their application or website more quickly. The same sort of principle applies here. Because all nodes, all devices in the hypergraph contain information about device location and IP address. So provisioning of resources to users and applications can be optimized accordingly. So let's talk about layer 0. So this basically is how DAG works in the context of the hypergraph. When a state channel is created, it can be integrated into the DAG channel by deploying an application chain interface. The state channel is created and then it's plugged into the L0. And when information is fed into that, they call it an emission. And basically the L0 substrate is fungible with the data that's being plugged into it. So here they describe how the flow for a purchase of access to information or modification of information. And basically, the request goes to DAG, funds are sent to the channel's account, the result is sent to the purchaser, and a checksum of the transmission is sent to the DAG network, which then unlocks the funds for the state channel. So the L0 is the underlying fungible layer that is interoperable. That's really what makes DAG an interoperability layer, because anything that plugs into it is fungible with DAG. And because they use information to model everything, it can plug into virtually anything. So thanks very much for watching. I hope that explains the hypergraph a bit. And if there's anything you don't understand, please feel free to reach out to me and we can have a chat about the DAG. Thanks.